Hello, ladies and gentlemen. Welcome back to day 4 of chapter 2. We are in section 2.2, day 2, normal distribution calculations. By the end of this video, you will be able to find the proportion of values in a specified interval in a normal distribution using table A or technology. Just so you know, table A is our standard normal probabilities table. We will get more into that in a bit. You will also be able to find the value that corresponds to a given percentile in a normal distribution using table A or technology. At the end of this lesson, I highly recommend that you work through these problems in our book. Right, let's get started. As I said, we are in section 2.2. This is day 2 of 2.2. We are dealing with density curves and normal distribution. You can read much of this information on pages 119 through 130 in your textbook. Now, the standard normal distribution, because all normal distributions are the same when we standardize, we can find areas under any normal curve using the standard normal distribution. Now, what is a standard normal distribution? The definition is that the standard normal distribution is the normal distribution with mean 0 and standard deviation 1 for standardized scores that follow a normal distribution. Basically, it means that we find the z-scores for all of the data points, and they will generally follow a normal distribution. So our center will be at 0, and our standard deviations go out 1 unit at a time. Now, the standard normal table, Table A, is a table of areas under the standard normal curve. The table entry for each value z is the area under the curve to the left of z. All right, now I'm going to actually show you this table in its entirety. You can find this at the back of basically any statistics book. This is the one for the updated 6th edition of the Practice of Statistics. You can see that we have this shaded region here where it says probability. This is the area. We often use it for probability. The table entry for z is the area under the standard normal curve to the left of z. We have all of these different decimal values to the 10,000th place, basically 4 decimal places after, or 4 place values after the decimal point. We have the integer and tenths place for our z-score, and then we have the hundredths place that we would add on here. So this would be negative 3.40, negative 3.41, negative 3.42, negative 3.43, and so on. And if you follow these across and then down to match up the tenths place with the hundredths place behind the appropriate integer, then you can find the area under that specific left tail for the normal distribution, so the area to the left of that value. Now, this is the way that we used to do this before technology really improved by leaps and bounds, and it's still very useful when you don't have a calculator. So I'm going to briefly kind of run through this a little bit more formally. Then we're mainly going to focus on using the calculator because in the current day and age, that's how we would expect you to actually complete these problems. But if your calculator loses battery in the middle of a test, it's useful to know how to use your non-calculator based tools. All right, so suppose that we want to find the proportion of observations from the standard normal distribution that are less than 0.81. All right, so 0.81 would be our z-score. All right, that's the boundary cutoff on the right-hand side. That's our right boundary, or our upper boundary. And this area would be going off to negative infinity. We need to find the right boundary within our table. So we would go down to where z is 0.8. So we're looking at these possible areas. And then the one right here would translate to the 0.01. It's basically 0.8 plus 0.01 gives you 0.81. So if we follow this down, this one right here would be our area under that curve. Right? So this area would be 0.7910. Right? That's why that's identified over here in the picture. Now, for normal distribution calculations, working forwards and backwards, we can answer a question about areas in any normal distribution by standardizing and using table A or technology. Now, the nice thing is that you don't necessarily always have to standardize, but let's start out looking at standardized values. So how to find the areas in any normal distribution. And something to remember is that the areas represent the proportion or the percent of values that fall within particular boundaries, which is why we find them interesting. All right, so step 1, draw a normal distribution with a horizontal axis labeled and scaled using the mean and standard deviation. The boundary values need to be clearly identified, and the area of interest needs to be shaded. All right, so you need to show this visually on every single problem where you need to find the area in a normal distribution. Now, step 2, perform your calculations and show your work. So you need to do one of the following. You either need to standardize each boundary value and use table A or technology to find the desired area under the standard normal curve, or we need to use technology to find the desired area without standardizing. Now, you need to be sure to answer the question that was asked. And an AP exam tip. Right, students often do not get full credit on the AP statistics exam because they use the option 2 with calculator speak to show their work on normal calculation questions. For example, saying normal CDF and then in parentheses negative 1,000, 6.84, comma 1.55. This is not considered clear communication because you haven't actually identified that you know what these different values mean. To get full credit, follow the 2-step process listed right here, making sure to carefully label each of the inputs into the calculator command if you use technology. For example, normal CDF, and then in parentheses, lower bound is negative 1,000, upper bound is 6, the mean is 6.84, the standard deviation is 1.55. You can use the symbols, or you can actually write down the words. Now, lower bound and upper bound don't really have symbols, so you do have to write those out. All right. Now, if you'd like to see how to use Table A further, please refer to your textbook for further information on using Table A, which is the standard normal table. I'm going to show you how to do this using the calculator. So find the proportion of observations from the standard normal distribution that are, to start with, less than 0.54. Now, because we're dealing with a standard normal distribution, that means a normal distribution with a mean of 0 and a standard deviation of 1. Essentially, you're finding the normal distribution made up of all the z-scores. So if I'm looking for less than 0.54, first I'm going to identify proportion of z-scores less than 0.54 is equal to. So I'm going to mark off the 0.54. I need to go less than, so I need to go to the left to find smaller z-values, and I'm going to shade that region. Right, so draw a normal distribution with horizontal axis labeled and scaled. I have my mean labeled. I have, I'm scaling by standard deviation, so my standard deviation is 1, so 0 plus 1 gives me a boundary of 1, and then 2, and then 3, and then same thing on the other side. I need to have 3 standard deviations above the mean, 3 standard deviations below the mean identified to have a completely labeled and scaled horizontal axis. Now, I've also titled this by showing that these are z-scores. Right, it helps you keep track of whether you're using the standard normal distribution or just a general normal distribution for a situation. I've kind of put a dashed line through where my boundary value is. My boundary value is that 0.54. I wrote down the 0.54. I made sure that it was actually between the appropriate values and then shaded to the left. Right, so this gives a visual representation of the area that I'm trying to find. Right, so the proportion of z-scores that are less than 0.54 can be found by using normal CDF. And normal CDF is basically calculating the integral to find the area under the curve. It's a calculus formula that we're using. Now, because this is non-calculus based statistics, we either need to use a formula in the calculator, or we need to use the table that we have in our book, which is also in your student resources packet. The only other alternative is going through AP Calculus before you take this course. Right, so in order to find this, we need to go to second vars to go to distribution, right, because we're looking at a type of distribution, a normal distribution. Normal PDF will find precise values, which basically gives you a line segment, and line segments don't have an area. That's why we go down to CDF, which is looking at a continuous set of values with a lower bound and upper bound to mark off the area that we're interested in. Now, DF stands for derivative function, and it's the normal derivative function for continuous values. Our lower bound is basically negative infinity. Now, on the calculator, it's negative 1 times 10 to the 99th power. That's the largest number the calculator can hold without overflowing. However, you could also just type in a very long and negative numbers. So you could put negative 9999999 if you wanted, or negative 1, 0, 0, 0, 0, 0, 0, 0, 0. It doesn't really matter. I tend to use the infinity values that the calculator starts out with just because I like to. If you want to do something else, just make sure that's sufficiently far from 0 on the negative end or sufficiently far from 0 on the positive end, depending on whether it's your lower or upper bound. That's the infinity. Now my upper bound is 0.54. My mean is 0, my standard deviation is 1, and I'm going to paste this in to the normal CDF function. All right, so once you hit paste, it actually types out the normal CDF, and then it shows those separate values. Now notice that what we had in the math type stats wizard blanks is basically what I've identified each one of these as. And then when we hit enter, I have 0.7054. I'm writing this to as many decimal places as we have in our table. Our table includes 4 decimal places, so I tend to include 4 decimal places. Because the 4 is followed by a 0, that's why I did not round the 4 up. I just cut it off. I truncated it at that point. Okay. Now, for letter B, greater than negative 1.12. Again, I had to sketch my standard normal curve, so mean at 0, standard deviations going out 1, 2, 3, and negative 1, negative 2, negative 3. These are z-scores. Greater than negative 1.12, so my boundary is at negative 1.12, which is just a little bit below negative 1. And then I need to shade to the right to go to larger values. Greater than means bigger than this number, and bigger values are found to the right. I wrote this as the proportion of z-scores greater than negative 1.12 is equal to normal CDF. My lower bound is negative 1.12 this time. That's my left bound. My upper bound, which would be my right bound, I don't really have one, which is why it's positive infinity. My mean is still 0, standard deviation is still 1. And if I go back to distribution, so second vars, and go to normal CDF, this time I want to have negative 1.12. I'm going to use 1 times 10 to the 99th. 0 and 1, paste it in. And that is how I get 0.8686. There's a 4 after the 6, so I leave the 6 alone. Let's move on to letter C. Now we're looking between 2 values. So if I'm still using the standard normal curve, that's why I have 0, 1, 2, 3, and then negative 1, negative 2, negative 3 on the other side of 0. These are still z-scores. My normal distribution, the shape of this curve is normal with a mean of 0, standard deviation of 1. And the proportion of z-scores between 0.49 and 1.82. Anytime you're showing an inequality where the value that you're looking for is between 2 values, the lower bound goes on the left, the upper bound goes on the right, because that's where they would be found on the number line. That's the order that they would be read in if you read from left to right. And z is found directly in between them. So this is the smallest number, which is why it has a less than sign pointing at it. Notice that this symbol opens on z, making z larger than it. But then the next symbol is pointing at z, making z smaller than this one. That's why this is the symbol language for in between. Just in case any of you have struggled with inequalities in the past. Now for my normal CDF, my left bound, my lower bound is 0.49. My upper bound, in other words, the boundary on the right, is 1.82. My mean is still 0, standard deviation is 1. And if I go back to normal CDF, so second vars to get to distribution, normal CDF, 0.49, 1.82, mean 0, standard deviation 1, paste, hit enter. We get about 0.277. Now after this 6 is an 8, which is why I rounded the 6 up to a 7. So I have 0.2777. Now if you wrote 0.2776, that's fine. Just make sure that you're consistent with whether you truncate values, meaning ignore the rules of rounding, or whether you actually follow through with the rules of rounding. All right, throughout this lesson, I have been following the rules of rounding. All right. Let's continue on to the next page. Now, the way that we find values from areas in any normal distribution. So we just looked at how to find the area. Now, what if you're given the area and you have to go backwards to the value? Step 1 is still draw a normal distribution with the horizontal axis labeled and scaled using the mean and standard deviation. the area of interest shaded, and unknown boundary value clearly marked. All right, so we need to first create a drawing. Then we need to perform our calculations and we need to show our work. You must show your work. If all you do is give me an answer, you will not get full credit. All right, so do one of the following. Either use table A, our standard normal probabilities table, or technology to find the value of z with the indicated area under the standard normal curve, then unstandardize to transform back to the original distribution. Or you can use technology to find the desired value without dealing with the standardized values. Be sure to answer the question that was asked. And as noted previously, to make sure that you will get full credit on the AP statistics exam, do not use calculator speak alone. For example, inverse norm 0.90, 6.84, 1.55. This is not considered clear communication. To get full credit, follow the two-step process, making sure to carefully label each of the inputs in the calculator command if you use technology. In step 2, which is inverse norm, area is 0.90, mean is 6.84, standard deviation 1.55. You do need to draw. All right, so back to example 2. A distribution of test scores is approximately normal, and Joe scores in the, now this should say Joe scores at the 85th percentile. All right, so we have a left area of 0.85 for 85% as a decimal. It's a left area because percentile is the area less than or equal to a boundary. And we have an approximately normal distribution. Now, how many standard deviations above the mean did he score? Now remember, our definition for a z-score is the number of standard deviations above or below the mean a particular data value falls. So this is asking you for the z-score and the interpretation of the z-score specifically. So for an area of 0.85, because I need to have my normal distribution sketched out, my mean of 0 standard deviation going out 3 standard deviations from the mean in both directions. How do I know where to put this boundary of z? How do I know that it should be just a little bit beyond 1? Well, we're going to take a brief time out here and we're going to take a look at the empiric rule for standard normal curves. All right. And something that I want you to kind of understand here is that in the middle here, we have, and let me see if I can zoom out a little bit. There we go. I'll zoom in here in a minute. So we have the standard normal curve area breakdown. So this is using the empiric rule, the 68, 95, 99.7 rule that we looked at in our previous lesson. Now, if you remember, 68% of all data values will fall within 1 standard deviation of the mean, which means that this area between -1 and +1 in the standard normal distribution is going to account for about 68% of the data values. Because the mean is the 50th percentile cutoff, that means that on either side of the mean is going to be exactly half of those area regions. So half of 68 is 34% on either side. Now within 2 standard deviations of the mean, this entire area between -2 and +2 is 95%. If we take 68% minus 95%, we get 27%. Cut that in half and we have 13.5%. I did the same thing between 3 standard deviations. Within 3 standard deviations is 99.7%. Minus the 95 here gives us 4.7%. There we go. Yeah, 4.7%. Even teachers need to double check their math every now and then. All right, half of that will be 2.35%. And then the final areas, the remaining 0.3% would basically be 0.15% on either side. If we start adding these up, to the left of -3 would be that 0.15%. So a proportion of 0.0015. If we're looking at 2 standard deviations below the mean and the left tail, that should be about 2.5% if we add both of these up, giving us 0.025. To the left of -1, Well, that should be about 16%. If we add up all three of these, you get 16%. You could also look at 68% subtracted from 1 is 32% for the total tails. Half of that would be 16%. Directly at the mean would be 50% to the left and 50% to the right. If you look to the left of a z-score of +1, so z less than +1, that would be this 50% plus the 34 here, which gives you 84%, which means that the 85% that we're looking for is literally just beyond the +1. Right? If you keep going like that, you can kind of fill in all of these breakdowns. I would highly recommend that you take a picture of this image so that you can refer back to it at will. Right, so let's kind of keep going. I'm going to be using that sort of content as we go through this. All right, so back to example 2. We had our normal distribution. Joe scores at the 85th percentile. Percentile means left area, 0.85. How many standard deviations above the mean did he score? We need z-scores. 85% would be just beyond, so it'd be the left area just beyond 1 standard deviation above the mean. So I put my right boundary here. That's the z-score that I need to find. So I've marked my unknown boundary value. And that unknown boundary value is going to equal my normal distribution being used in reverse. Normal CDF is going forwards. Going backwards, we need to use the inverse of that operation, which is why we're literally using inverse norm. All right, an inverse norm requests the area, the mean, and the standard deviation so that I can identify the cutoff value. Now, in these newer calculators, these thinner ones that like TI-84 plus CE, they have an option for which tail or which area section you are referring to when you're referring to area. Older calculators don't have that option, and you always have to use the left tail. I would suggest leaving it at the left and working with it from there. All right, so my area is going to be 0.85, mean 0, standard deviation 1, and we have a z-score of 1.036 approximately. You could make this 1.04. I tend to go out to a few more decimal places than are necessary, but you need at least 2 decimal places after, at least 2 place values after the decimal point. All right, so this is the z-score, but let's finish answering the question. How many standard deviations above the mean did he score? Joe scored 1.036 standard deviations above the mean test score. For letter E, in a normal distribution, so I put capital N here to remind myself the shape is normal. First quartile, which happens to be the 25th percentile, which means a left area of 0.25. So the first quartile is how many standard deviations below the mean. So what they're really asking me to do is identify the z-score that cuts off a left area of 0.25. That's why I have these different sections circled or underlined, and I'm identifying the different details that that specific information provides me with to be able to go through to answer my question. So I've sketched out, again, the standard normal distribution, mean 0, and then adding 1 for each of my standard deviations going above the mean and then below. And an area of 0.25, when you're 1 standard deviation below the mean, that cuts off an area of about 16%. So 0.25% will be between the 0.16% and the 50%, so the 0.5. So between 0.16 and 0.5 is where 0.25 will lie, probably closer to the 0.16 than the 0.50. And I have my z-score here in the middle. Right? So I have my area identified, I have my boundary identified, this is scaled, labeled, and then I can go through and find that area, or use that area to find what this boundary really is. So z is going to equal inverse norm. My area is 0.25, mean 0, standard deviation 1. You go ahead and input this. So second vars gets me a distribution. Go down to inverse norm. I'm going to zoom back in because I realized that I forgot to do that. And let me get us back at, there we go. Sorry about the shaky camera for a minute. And we're back. All right, so area 0.25, mean 0, standard deviation 1. This is a left-hand area because it's a percentile. Paste it in. And I have negative 0.64. I just left it as negative 0.64. You could make it negative 0.67. You could make a negative 0.674 if you wanted. You could go out a little bit further, at least 2 decimal places. All right, the first quartile is 0.67 standard deviations below the mean. All right, that's where it's located. The first quartile is located 0.67 standard deviations below the mean. Below the mean is where this negative sign is being represented. So the negative sign became a verbal description of where this value is actually located along the number line on which side of the mean. Right? I know this video is a long one, but I wanted to go into detail on these calculations. Right? So we're going to continue on. Now for example 3, according to the CDC, the heights of 12-year-old males are approximately normal, so approximately normally distributed. I put a capital N there. With a mean of 149 centimeters, that's our mu, and a standard deviation of 9 centimeters, that's our sigma. All right, so I have our mean and our standard deviation identified with their symbols. I have the shape identified, which is how I put together a normal distribution with a mean of 149, standard deviation of 9. And for letter A, what percent of 12-year-old males are less than 160 centimeters tall? The what percent is asking you what area is less than 160 centimeters tall in this distribution. The height of 12-year-old males is what X represents, so X is the height in centimeters. So the proportion of X values less than 160 in this distribution. I wrote out my number line, I drew my normal curve above it, I scaled it with my mean in the center, and then I added 9 each time to get each of these values. So 149 plus 9 is 158. 158 plus 9 is 167. 167 plus 9 is 176. All right. I did the same thing on the other side, but subtracting. 149 minus 9 is 140. 140 minus 9 is 131. 131 minus 9 is 122. Notice that I also titled this with height in centimeters. And in order to go from boundary to area, when area is what you're trying to find, you're going forwards, which is normal CDF. So my normal CDF, my lower bound is going to be off to infinity because less than doesn't have a boundary on the left. You're constantly going smaller. But it does have an upper boundary. I need to know what I'm going less than, which means my upper is 160. Mean is 149, standard deviation 9, and I'm going to type that in. So second vars to get to distribution. And I'm going to type in, see, I have my negative infinity already in there. That's that negative 1 times 10 to the 99th. The E is the calculator scientific notation, version of scientific notation, basically. My upper bound is 160. My mean is 149. Don't forget to change these. Standard deviation is 9. If I paste that in and calculate, I now have 0.8892 approximately. That 8 would round the 1 up to a 2, or you could truncate it. That's where I'm getting my 0.8892. Now this asks me for the percent. So I need to go from this proportion, multiply by 100 to get my percent. All right, so this times 100 gives me 88.92% of 12-year-old males are less than 160 centimeters tall. That's how this value is turning into this sentence. Letter B, what percent of 12-year-old males are greater than 145 centimeters tall? Again, it's asking for area. So I have my same distribution written out here. I have my boundary at 145. I need to go greater this time, which means I need to go to the right because that's where larger values are found. All right, so 145 is the lowest. I'm going greater than that. So I'm finding the proportion of heights that are greater than 145. My normal CDF is going to be given a boundary, a lower bound, so a left bound of 145, an upper bound, a right boundary of positive infinity because I didn't give an upper level to this. It just keeps going greater. A mean of 149 still and standard deviation of 9. And if I fill this in, second vars, go to normal CDF. Now I'm using 145. 1 times 10 to the 99th is my upper boundary. If I paste this in, I get 0.6716 approximately. That's where this came from. So 67.16% of 12-year-old males are taller than 145 centimeters, right? This number times 100 is where this percent came from. Okay, let's go on to our last page of calculations because I want to show you all the different ways that we are required to play with this, all the different things that you might see. All right, so for letter C, what percent of 12-year-old males are between 140 and 160 centimeters tall? Now, again, this is an area. I'm still using my normal distribution with a mean of 149 and standard deviation of 9. And between X is going to have the less than symbols on either side of it in order to be able to fill in my proportion. I scaled and labeled my number line. I have my curve drawn above it. My left boundary at 40, my right boundary at 160. Right? Notice that I actually wrote in the number when it wasn't one of the data points already on the number line. And normal CDF, lower bound is 140, upper bound is 160. My mean is 149, standard deviation 9. And if we go through to calculate, second vars, go to distribution. I have 140 as my lower bound, 160 as my upper bound, still using the same mean and standard deviation. And I have 0.7305 approximately. Right. Multiply by 100, and 73.05% of 12-year-old males are between 140 and 160 centimeters tall. The only reason I'm calculating this as a percent is because I was asked to. If I was asked what proportion, then I would leave it as the decimal. Right. Only a couple more. What is the 85th percentile of heights for 12-year-old males? Now, 85th percentile is telling you that the left area from your boundary is 0.85. Right? Basically, the left boundary is 85, to the left of the boundary is 85%. So you're looking for a right boundary. We're still using our normal distribution with a mean of 149, standard deviation of 9. I have that labeled and scaled down here with my X identified over here. Now remember, previously we had gone through a standard normal distribution with an area of 0.85. That was just beyond one standard deviation above the mean. 158 is one standard deviation above the mean in this distribution, which is why I marked this off where I did. Right? Think about where that area should be found approximately between what values that boundary should be located so that you can give an accurate graph. Right, now this time, I'm given the area and I need to go backwards to the boundary. This is the reverse of what I've been doing for the last 3 problems. I already have the percent. That's why I need to invert what I've been doing and use inverse norm. So instead of normal CDF, now I'm going in reverse. So inverse norm, my area of 0.85, mean of 149, standard deviation of 9. This is my left tail, my left area. Paste that in, and I have 158.33. All right, so 158.33. That 7 rounds the 2 up. So the 85th percentile of heights for 12-year-old males is at about 158.33%, or 33 centimeters. Now, you could also do this with a standard normal distribution. If we use the z-score that we had found previously, we already know the mean and standard deviation, and we knew the z-score from a previous problem. We could enter that z-score into z, the mean into mu, the standard deviation into sigma, and solve for x. If we put this over 1 and cross multiply, we end up with 9 times the 1.036 equal to x minus 149. Now remember, that 1.036 came from letter D back on the previous page. Right, we had already found how many standard deviations above the mean the 85th percentile would be in a standard normal distribution. So I'm just using that number. Right? If I add the 149 to both sides, then I get 158.324, which is very close to the answer that I just got using the calculator. So you could do this either way. Right? You could use standard normal distribution, or you can just use the regular distribution working backwards. Right? So there are multiple methods for this. For letter F, what is the value of the first quartile for 12-year-old males? So value, it's asking me for the x value, so it's asking me for a height. First quartile implies that there's a left area of 0.25 because this would be the 25th percentile. All right, so I'm back to what I was doing before, and again, 25th percentile is going to fall between the 16th and the 50th, which would be between one standard deviation below the mean and the mean, so between the 140 and the 149. That's why I have X marked off right here. And my area is 0.25, so I'm going to use inverse norm, area of 0.25. Mean of 149, standard deviation of 9. Paste it in, and we have about 142.93 centimeters. All right, so the first quartile for 12-year-old males is at about 142.93 centimeters. That is the boundary that would cut off that lower tail. And the final one that I want to show you is how to work totally backwards. All right, so suppose that the mean height of 13-year-old males is 155 centimeters. So 31% are taller than 160 centimeters. And that the distribution of height is approximately normal. What is the standard deviation of height for 13-year-old males? All right, so let's break down the information we have. Suppose the mean height of 13-year-old males is 155 centimeters. We have mu. 31% are taller than 160 centimeters. We know the proportion of values greater than 160 is 0.31. The distribution of height is approximately normal. We know the shape. What is the standard deviation of the height for 13-year-old males? We're trying to find sigma. Now, you can find Z, you can find a boundary, and you can find area using the normal distribution. But in order to find mean or standard deviation, you're going to have to work backwards from the Z-score formula. So you're going to have to work with Z-scores. That's why I'm going to use the standard normal distribution here. If my right area is 0.31, my left area is 0.69. Remember, the thicker calculators, the older ones, only use left area, so it's important to identify both areas depending on which calculator you have. My Z-score that is going to cut off this left area of 0.69, all right, I can find by doing inverse norm, area is 0.69, mean 0, standard deviation 1 for standard normal distribution. So 0.69, 0, 1. And if you do that with the left tail, if I was to do this with 0.31 with the right tail, I want to show you that these would turn out the same. So if you have a newer calculator, you can actually identify where your area is, and it can make your life a little bit easier, right? But this kind of technological writing, you'd also have to have comma, and then you'd have to tell me which tail area you were dealing with. So where the area actually is. All right, if you just write it this way, it's assumed that this is the left area, so be careful with that, right? I almost made a mistake with that earlier. So I have 0.4959 approximately. All right, now that's my Z-score. So that's what I'm going to put into here. And now I have 3 pieces of information that I need. My X value, the boundary, is the 160. So that's why I have 160 here. My mean was 155. My standard deviation is the unknown, but I know the Z-score that this calculation would produce. If I put the Z-score over 1 and cross multiply, I end up with 0.4959 times sigma equals 5. 160 minus 155 is 5. Then to undo the multiplication on this side, I need to divide by 0.4959 on both sides. If you take 5 divided by 0.4959, your standard deviation is going to be approximately 10.08 centimeters. All right, now this video turned out to be quite long, but I hope that how far I broke this down and the detail with which I showed the problems helps you to be able to complete these problems. All right, try these yourself, and I will see you in class.